Good morning. I find this conference timely, thinking that thermodynamics provides us with a comprehensive worldview, particularly of the world we view in distress of climate change, loss of biodiversity, and global-scale pollution. So I'm grateful to the organizers for granting me this opportunity to re-examine the foundations of thermodynamics and reveal the resulting wide vistas. The laws of thermodynamics are thought to be universal. However, while each law states a fundamental fact, none of them explains the stated fact. Specifically, the first law does not explain why energy is conserved. The second law does not explain why entropy never decreases. The third law does not explain why entropy tends to zero as the temperature approaches absolute zero. And the zeroth law does not explain why two systems in thermal equilibrium, with a third one, are also in equilibrium with each other. In the tradition of science, it is not a law, but a theory that explains. The law only states a fact inferred from data, whereas the theory provides a viewpoint to make sense of data. Moreover, a proper theory derives from an axiom, not from data. Consequently, the theory can be falsified with all of the data. In contrast, an effective theory, that is, a mathematical model, is matched with data and hence cannot be falsified with that data. So, what is the universal axiom that underlies the universal laws of thermodynamics and explains data? Ludwig Boltzmann and Willard Gibbs were after such an all-encompassing thermodynamic theory. They devised statistical mechanics, assuming everything comprises the same basic building blocks. Boltzmann adopted this ancient atomistic axiom, also favored by Newton and Galilei. Surely, we know by today that the atom is not an indivisible permanent element. This was not new to Boltzmann either. The discovery of the electron proved the point already at the end of the 19th century. However, even the more recent discoveries of quarks and other subatomic particles do not invalidate the atomistic axiom, but only leave us ignorant about what is the fundamental element. Of course, we are not all ignorant. We can infer from phenomena such as annihilation and pair production of particles and antiparticles that everything comprises quanta of light. Indeed, in 1926, Gilbert Lewis renamed the light quantum, thinking that the photon is the universal atom, the constituent of everything. Already earlier, Isaac Newton had reasoned from emission and absorption that matter and light are convertible to one another. Nevertheless, one might think that the photon conservation would have been refuted long ago, since it is not stressed in textbooks. For example, in quantum field theory, the photons are created out of nothing and annihilated into nothingness. However, the raising and lowering operators only mimic or model transitions from one state to another, but do not correspond to them. Namely, photons do not emerge from nothingness or vanish into nothingness, but emit from matter and absorb into matter. Likewise, abstract spacetime is not a true account of space, but a geometric model of the physical substance of space. The role of space cannot be disregarded in any theory because everything is immersed in it. Moreover, it's worth emphasizing that the Michelson-Morley experiment did not negate a light embodying, hence relativistic, quintessence. On the contrary, it only disproved the light-carrying medium, the luminiferous ether. So the vacuum cannot carry light, but still it can be light. Specifically, consider two photons paired out of phase. By pairing, these photons do not vanish altogether. They only cancel each other's electromagnetic effects. Such omnipresent substance is transparent and hence hard to detect. Yet you can sense space in terms of inertia and gravitation without sophisticated scientific instruments by your own body. Most importantly, space bears the characteristics of a light-like vacuum. The squared speed of light is equal to the product of vacuum permittivity and permeability. And the squared speed of light is also equal to the gravitation of all mass in the universe. This thermodynamic balance between the vacuum and all matter is a full proof that everything comprises photons. How else would the balance be gained if not by the exchange? A photon carries energy on its period, hence absorption and emission are means of attaining thermodynamic balance. Backed up with this insight of the axiom of everything comprising photons, we proceed now to formulate statistical mechanics as the universal theory that underlies and explains the laws of thermodynamics. To this end, consider an energy level diagram where all entities are made of the same fundamental constituents. Accordingly, a transformation from one entity into another entails a change by at least one quantum. For example, a chemical reaction proceeds from substrates to products by either absorbing or emitting at least one quantum of light. Likewise, an electron may break into W- boson and a neutrino, a one quantum particle. The axiom that everything comprises quanta is essential because it allows us to draw the general energy level diagram and formalize it as an equation of state, even without explicitly knowing the composition of entities. In a sense, this diagram presents all options while any specific system displays only a fraction of all quanta and only a limited set of transformations. For example, a cell accommodates a limited number of molecules and achieves a limited number of chemical reactions. Likewise, a star possesses a limited number of particles and performs a limited number of nuclear reactions. Yet, the molecules and particles comprise photons, and their reactions are fundamentally transformations of photons from one molecule or particle to another. Let us focus on one entity and ask what it takes for that entity to exist. Clearly, the entity could not exist if any one of its ingredients were missing altogether. Thus, we may quantify the existence in terms of a mathematical product of the ingredients. The multiplicative form ensures that the probability of existence is 0 if any one of the ingredients indexed with K is missing. Conversely, the probability of existence is high when the ingredients numbered by Nk are numerous and the energy difference delta GJK between the K ingredients and the J product is small. Then the balance can be shifted from the substrates toward the product by absorption or emission of photons with energy difference delta QJK. For example, sunlight drives the conversion of carbon dioxide and water into sugar and oxygen. Likewise, we may quantify the existence of a whole population of J products as a mathematical product. Again, the multiplicative form ensures that the probability of that particular population is 0 if any one of the J products is missing. For example, if any one of the photosynthesized sugar molecules is missing, the population of them is not exactly complete, so it does not exist properly. Here, the probability is divided by the factorial because the order of indistinguishable members is immaterial. Finally, we may quantify the existence of the whole system comprising various entities as a mathematical product over all populations. Again, the multiplicative form ensures that the probability is 0 if any one population indexed with J is missing. For example, if any one population of the numerous molecules making a cell is missing, the cell does not exist exactly like the whole system. It follows from the all-inclusive axiom that the presented formalism is general. It applies to any system and any transformation, from elementary particle reaction to the expansion of the universe, from a chemical reaction to biosphere, from a small purchase to world trade. Probability is an all-encompassing concept. It counts all quanta of the system. However, we are used to additive measures instead product forms. So, let us take a logarithm of the product to obtain a sum. For historical reasons, the sum is known as entropy when multiplied with Boltzmann constant, Kb. For the same reason, the average energy is known as temperature multiplied by Kb. This equation of entropy multiplied with temperature is the state equation. It expresses the energy bound in the entities numbered Nj and the energy given by differences, the delta terms. This energy is free for the populations of entities to change, and so they will. Taking the time derivative from the state equation yields the equation of motion. It shows that free energy drives changes from one state to another until free energy is consumed altogether. Then, at the thermodynamic balance, entropy is maximum as all energy is bound in the populations. Free energy drives changes in populations. The rate of a population change is proportional to free energy by mechanisms that facilitate flows of energy. For example, a catalyst speeds up free energy consumption. Flows of energy distribute among alternative paths to attain thermal equilibrium in the least time. Thus, in the words of Darwin, flows of energy naturally select paths of least time. So entropy does not only increase, it increases in the least time. Surely Boltzmann knew that the second law of thermodynamics and the principle of least time are related, but failed to figure out exactly how. He openly acknowledged this failure in his address at the decennial of Clark University. The derived equation of motion for quanta can be written approximated by a continuous equation of motion by replacing the discrete chemical potential with continuous scalar potential, and likewise the discrete dissipation with continuous vector potential, and substituting the total energy with kinetic energy. The continuous equation of motion can be derived from the Newton's second law in its complete form as well, where the force equals a change in momentum by multiplying it with velocity. At the stationary state, dissipation vanishes and evolution reduces to steady-state circulation known as the virial theorem, where the kinetic energy balances the potential energy. Thus, the equation of state and the equation of motion derived from the axiom of everything comprising quanta reproduces the familiar formula of stationary state physics. Finally, it is perhaps worthwhile to take a glimpse at quantum statistics as well. The renowned distribution of photons can be derived from the energy level diagram of the vacuum. Here, photons distribute among the trains of paired photons that comprise the vacuum. Again, the probability contains the exponential term to express that the high energy photons are rare and that the low energy ones are abundant. As there are two options for each locus, there is the factor 2 in the denominator. Then working out the stationary state equation yields the familiar distribution of Bose-Einstein statistics. Let us now summarize how the equation of state and the equation of motion explain the fundamental facts stated by the laws of thermodynamics. First, energy is conserved because its carriers, the photons, are permanent. On the other hand, energy is not conserved because the photon shifts frequency as it propagates from one medium to another. For example, the photon shifts red when it propagates to a weaker gravity. So, the true fact is that photons are conserved, not energy. Second, entropy cannot decrease because free energy can only decrease. Squaring free energy by inserting the rate equation into the equation of motion proves the point. So, the true fact is that everything evolves toward balance, where entropy is maximum and free energy is zero. Third, when the temperature tends to absolute zero, also entropy tends to zero because entropy is a function of energy. Physically speaking, entropy vanishes when energy vanishes because entropy enumerates entities that carry energy. Forever redshifting photons approach nothingness. So, the true fact is that energy does not exist as such, but is always embodied in photons. Finally, the zeroth law about the mutual balance is inevitable. Two systems end up in thermodynamic balance when energy flows through a third one. So, the true fact is that everything depends on everything else. In this way, statistical mechanics of open systems explains the laws of thermodynamics, but more importantly, it explains observations. So, what do the observations tell us? Quite remarkably, data look all the same irrespective of scale and scope. Specifically, it has been noticed ever since Galilei that central parts of the sigmoid curves follow straight lines on log-log scales. In other words, power laws are ubiquitous. The sigmoid curves in turn sum up skewed distributions, and statistical mechanics makes sense of the skew in distributions. It is a consequence of the least time free energy consumption. This is proved by expressing an entity as a product of the fundamental elements and taking a logarithm. Then variation in the number of fundamental elements is seen as log normal, that is, skewed. Fat tails extend way beyond normal distribution. For example, by the normal distribution, big fish are bigger than expected from the average fish. The reason is obvious. The biggest fish produce the most egg, whereas the smallest ones get eaten up. The imperative to attain balance in the least time drives the flows of quanta through functional structures, such as fish. Thus, the emergence of animates can be understood to follow from the quest to attain balance in the least time. Flora flourished for matter to gain balance with sunlight. Fauna flourished to gain balance with flora. Likewise, the emergence of economic machinery can be understood as a manifestation of gaining balance with the supplies in the surroundings. Fossil fuels are extracted for economies to gain balance with their energy content. The skewed distribution of energy transduction mechanism is optimal when it channels flows of energy in the least time. Accordingly, the most effective means are scarce as they are costly. Conversely, the least effective ones are abundant as they are inexpensive. Speaking in biological terms, this least time quest, resulting in various skewed distributions, displays itself in competition and collaboration. However, these are not exclusive characteristics of ecosystems and economic systems, but likewise also physical systems display competition of opposing forces and cooperation of parallel ones. For the same least time reason, standards and conventions emerged as means to consume free energy. For example, amino acids are not mixed-handed but single-handed because protein synthesis using standardized substrates provides faster means of consuming free energy. Likewise, assembly lines require standardized pieces. Moreover, for the same reason as we shake hands with our right hand, we use right-handed screws, and we drive on the same side of the road. Otherwise, things would not work. That is, free energy would not be consumed effectively. Likewise, we may reason that matter dominates over antimatter to make things work. For example, the standard of matter allows nuclear reactions to happen. Intriguingly, the derived equations also disclose that evolution toward thermodynamic balance is a non-deterministic process. Future lies open as equations are non-integrable. Motions cannot be separated from their driving forces. In line with our own experience, opportunities to consume free energy open up while others close in as the system evolves from one state to another. The paths can be calculated exactly only at the balance where energy is conserved. Now that statistical mechanics derived from the atomistic axiom, familiar to Boltzmann, delivers thermodynamics consistently with data and in agreement with common sense, it seems somewhat puzzling why did Boltzmann not formulate it? Why did he end up with statistical mechanics that applies only to stationary or closed systems? What went wrong? It seems that on the one hand, knowing in advance the state of balance, Boltzmann forced the condition of balance instead of recognizing that forces that drive the system toward balance. After all, Boltzmann had derived the renowned velocity distribution of gas molecules, so he knew the outcome of evolution to thermodynamic equilibrium. Accordingly, his equation is devoid of free energy without the photons that either absorb or emit in any transformation. Moreover, Boltzmann might have also been after an integrable equation. In other words, he might have been biased toward deterministic equation of motion. Perhaps he did not even consider that nature is non-deterministic yet not indeterministic, that is, random. On the other hand, Boltzmann recognized the statistical nature of motion as he employed probability concept. However, he erred by adopting random acausal symmetrical distribution instead of non-deterministic causal skewed distribution. While the Gaussian distribution is convenient for calculating, it is not an accurate account of reality. Natural processes are not arbitrary, but forced toward balance in the least time. Therefore, the distributions emerged with skew. The least time quest to consume free energy can be understood as natural selection. Boltzmann was after this insight, but failed to put Darwin's words in thermodynamic terms. Today, we might think of this generalization from biological to universal as audacious step. However, Darwin himself generalized natural selection from artificial selection, that is, breeding selected by man. Moreover, Darwin did not recognize any boundary between animate and inanimate. In a letter to Joseph Hooker, Darwin wrote, "If we could conceive in some warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, that a protein compound was chemically formed, ready to undergo still more complex changes." So, troubles in thermodynamics originate from Boltzmann failing to formulate statistical mechanics properly and from his successors accepting the faulty theorem. Subsequent attempts to expand the stationary state evolutionary formulation could not but cause obscurity. In contrast, the presented evolutionary equation naturally limits to the stationary state where the balance has been attained. Conversely, it is eye-opening to many a biologist that evolution is nothing but happening. Quanta carry energy on their periods of time, thus the flow of quanta embodies the flow of time. However, the flow is not arbitrary, but takes the course of least time, equivalent to the maximal free energy consumption. Among the common misconceptions, particularly problematic is the association of increasing disorder with increasing entropy. By common sense, disorder, just like order, is not a cause but a consequence of evolution toward balance. For example, think of disordered water freezing to orderly ice to attain balance with cold surroundings. Likewise, over the eons, the inanimate matter has assembled and organized into biota to gain balance with a high energy insulation. Moreover, consider Shannon's concept of information entropy. It treats information as if it was immaterial. However, no information exists without embodiment. By common sense, information is free energy. It enables motion, evolution toward balance. All this might seem naive compared with sophisticated theorization. Even so, what is real is compelling in the end. A paradigm shift entails a shift in perspective, not a change in the phenomena themselves. For the proposed axiomatic perspective, phenomena follow one and the same principle. It is about asking why things happen and answering. Motion follows force. A rock falls down. A plant grows toward light. It is also about asking how things happen and answering. Motion takes the path of least time. For example, rock falls straight down. a plant grows straight to the light. Of course, it seems pertinent to press that the new perspective ought to be precise in its predictions. As usual, the precision increases by including ever finer details. However, precise predictions, as explained, are unreal because motion affects its driving forces and so on. Only steady-state motions are computable. Also, predictions in the past have in fact been calculations of this kind rather than true prophecies. For example, a closed orbit can be calculated, whereas an open trajectory remains intractable. Complexity is not the obstacle per se. For example, the problem of three bodies is inherently intractable because everything depends on everything else. In conclusion, science is supposed to make sense of reality. Sense-making means comprehension through our own senses. This empirical stance may seem unwarranted, as our eyes register only a narrow band of the electromagnetic spectrum, our ears only a slim strip of vibrational spectrum, and our nose and mouth only a small assortment of molecules, and our skin only a limited range of temperatures and pressures. However, regardless of scale and scope, data look all the same and warrant relating any phenomena to our experience. To this empirical end, the axiom of everything comprising photons allows us to formulate an all-encompassing theory. Not too surprisingly, the holistic tenet underlies the universal laws of thermodynamics. Most importantly, the derived equation of motion reveals the essence of explanation, namely causality. A force is a cause, and a change in state is a consequence. So we should strive to sense forces, whatever kind, to navigate along their resultant. Otherwise, dismissed dynamics, now evident in climate change, the loss of biodiversity, and global scale pollution will put us in peril. Science complies facts about nature, but at its best, science revises our aberrant thoughts about nature into those that are natural. Thank you for your attention.